Hello, I'm Martin Sucha. I work as a staff engineer at kiwi.com, and I work in a team that stores data in a database, and we have about a million database requests per second, so we sometimes have to debug performance issues. Also, I contributed some features to GoTrace UI, namely GoRoutine counters and task support. You will see later a demo. So, what is the agenda for this talk? First, I will tell you why do you want to use runtime traces, and then how you can record the data. Why is it better than 2 years ago? And then I'll talk about tools that you can use to view the traces, and there will be a demo of GoTrace UI. So, why would we want to use traces? When you are debugging an issue in production, and there is an issue with latency, for example, you have a latency spike, then you have multiple tools that you can use. Obviously, you can check, have I released something recently? And if no, then you can check other things like logs. And if you have a spike, you see that, oh, there is an error with a timeout. But that doesn't really help you if there are logs from all the request types or all the database queries that you make. There is also, you can use runtime traces, but you see about the same thing. It's really high level. You can look at metrics, and metrics have a resolution of 1 data point per 10 seconds. And if you have a request in your application, it's usually less than a second, right? So a lot can happen within 10 seconds. You need a different tool. And runtime traces are the tool. You can really zoom into what the application is doing. So one of the things that the application is doing and the runtime is doing is actually running your program. So what it does is takes your GoRoutines and schedules them onto processors, which then run onto operating system threads, which are referred to as machines in the runtime. Now, runtime traces are a log of what the runtime and your program does. So whenever a GoRoutine changes its state from it's created, it's running, it's assigned to a processor, or it's ready to run, but it doesn't have any processor to run, everything like that is recorded in the runtime trace. So when you display this in a tool, it looks like a spans of what the processors are doing, and you have all the events like start, stop, and what crucially you also have are the places where nothing is happening. So that could be because everything is blocked on some mutex or some other conditions. Then there are other things in the runtime trace. There are events for when the runtime stops the world, so that you can distinguish it from the other gaps there. It happens, for example, if you read the memory statistics, the runtime has to stop all the GoRoutines to be able to read a consistent view of it. Then there are events about garbage collection, like when it started, when it stopped, which processor was used to run the garbage collection phases, and which GoRoutines were assisting the mark phase.
Martin, you might need to fix the microphone.
Sorry?
We might need to fix the microphone.
Okay. Okay, is it better? Right. So another thing that runtime traces contain are regions, which are your user annotations. So you can mark parts of a Go routine and create a span about what it is doing. The regions have a limitation that they have to be nested correctly. And you can have multiple levels. And each of the regions has to end before the Go routine ends. Then you have a more high-level span that you can create. There are tasks, and tasks can have parents. So each of those sub-steps that the program is doing can point to the top-level one, and when you are viewing the trace, you can also refer back to them and navigate through this entire state. Also, the task can be longer than a single Go routine when, for example, you need to do a cleanup when it ends. There are also another kind of user annotations. There are logs. So what you can use is that, say, you associate a task with a request ID you have. So you can correlate your logs or distributed traces or whatever. There are also some experimental events that you can enable. For example, there is a Go debug flag for that. You can enable logging of all memory allocations if you are brave enough to run this in production. I probably wouldn't. Right, so as you can see, you can record a lot of data in the trace, and the volume can be quite big. For example, a trace that I have captured is about 60 megabytes for 10 seconds of data, which is 50 megabits a second. Now that is from just a single application pod. If you have a lot of pods, that could quickly become like a big volume. So how can you record stuff like that? Well, just, does the recording have any performance impact? Just 2 years ago, the performance impact was about 10% of latency and 10% of lower throughput when you enable the traces. But then in Go 1.21, the capture of runtime traces was optimized. So it takes just about the percent of latency and percent of throughput. So we can easily run this in production and not be worried about it. And another thing that changed, that was in Go 1.22 about a year ago, is the format of the traces. So before we had just a single, like a block of a file. There were batches. Each processor can write to its local buffer. And then when you stop the recording, or like when the buffers were full, they were flushed as batches into the file. Now, an issue with this is that when an event happens sometime when you start the recording, and the processor does not fill its buffer, like this one, at the end, the event from start can be at the end of the file. Now, why this is a problem? Because when you process the file, you have to read it all into the memory, and you don't have any guarantee about the events appearing in a timely manner. So what changed in Go 1.22 was that the file was split into multiple generations, and also the buffers changed from per processor to per machine. But for us, what is important is that there are multiple generations, and this guarantees that once in a while, we know that any event must be here, and an old event cannot be in the next generation. So what this allows is that you can start recording, and then you discard all those generation. And in this way, you can keep only the last, I don't know, like 10 seconds or what you say or amount of data in the buffer. So you start recording, and when something happens, like there is a latency spike, you can write the data in the buffer you have, and then you have a recording of what just happened. Before, when we did not have the flight recorder, you could only hit start and stop, but it wasn't clear when to start recording because you want to record a few seconds before an issue happens. And another thing that this allows you to do, or I would like to share, so this is the flight recorder. It was added in Go 122, and also it was accepted. The proposal to add this directly to runtime was accepted in January this year. Now, you could also this flight recorder, when your program crashes, it doesn't keep the buffer. So could we make a flight recorder that keeps the data, like when you have out-of-memory kill or when there is an issue in the program? And this is something I've been playing with, but I don't have any results from this experiment, just like half-written code. But I think the idea is also interesting, so I wanted to share it with you. We could do a different kind of flight recorder that writes the data in a buffer in our application, and then it shares it with another helper application. And when the main service is killed, the helper application, keeps the buffer in memory and can write it somewhere else. But for this to work, we will need to add support to be able to read truncated traces. Another thing that we used a few years ago, we had an issue that we had Go routines that were leaking, and we used something like a flight recording, but the flight recorder was not available there. So when we detected, we started the timer when a request came, and after a minute, when we detected Go routines belonging to this request, we dumped the stack with debug stack, and the Go routines that were running for 1 minute were the ones that probably leaked. And nowadays, if we wanted to do something like this, we could use the flight recorder instead. So we now have recorded the trace, and we need to read it. We need to find out what the issue in the program is. So since the beginning, since 2015, when the runtime tracing was added to Go, there was a built-in tool for this, which is the Go tool trace command. And when you run it, it splits the traces by processor. It also has some features to display histograms of latencies, stuff like that. So what happens when you click one of those links is that an UI opens. It looks like this. And you can see that there are some warnings when you open it in Chrome nowadays, because when they added it in 2015, it was taken from Chrome. This was a tool for visualizing traces in Chrome. And what they did was they showed the Go traces into it. So this tool wasn't built specifically for Go, and since then, Go, like the Chrome team, moved on, created a different tool called Perfetto. There were some experiments with using this tool for Go, but it didn't materialize. There were some issues. So the built-in tool is stuck with this old viewer. So instead of using this, you could use a different tool called GoTraceUI, which Dominic Honef created about 3 years ago. I think the first release was 2 years ago. So when you are going to try this, you can get it from the web, or you could get it from GitHub and build the main branch. And I recommend you do that because the latest release was about a year ago, and it doesn't support the latest Go version, as the traces have version numbers in them. So Dominic is currently busy writing a new UI framework for Go, because this uses GeoUI, and I think that's because there is no release, as he's focusing on that. Anyway, let's go to a demo. No. Okay. So I will zoom this. Doesn't work. Okay. All right. So there is a trace that I captured a while ago, and at the top you can see the timeline with the time in the trace. You can see the garbage collection metrics, so heap size and the goal. Below that, you can see number of Go routines. It will get better when we zoom in, as it uses some algorithm to reduce the data points when you are zoomed out. So let's zoom, for example, about here. And there are the metrics. There is a state of garbage collection. There is a timeline for stop the world. So you can see that the application is reading memory stats about half a second. Each garbage collection also has stop the world at the beginning, at the end. There are the processors. What are they doing? At this point, you can see there is a garbage collection happening on 3 of them, and also the application is quite busy. It's doing a lot of CPU work. And currently we are zoomed at like 100 milliseconds, but we could zoom into really to nanosecond level. So you can zoom and view state of each processor, what it was doing, state of the Go routines. You could scroll to the Go routine and see its timeline, which is nicer than in the old tool, because there you had to wait for it to process data. So in this tool, you have everything in one place. So let's zoom out a bit. And we could, for example, take a look at a request that was taking the most time. So, for example, this one. We could then scroll to it and see the logs for it, so I can see which user agent it was, or the database request it was doing. In this case, you can see there is a different task just below it, and it says decode. That's because we have tasks in our code that split the parts of the request. So from this, I can see that most of the time it was just reading the request from the client, and at the same time I can go with home at the top and see that there is not a lot of CPU activity on the processors. So the issue is probably with the client. I can navigate to all the database requests. There is a different task. Oops, sorry. Seems that this one doesn't have. Okay. We can check the stack traces that are recorded in the. So when I press S, the timelines expand, and you can see all the captured stack traces in the processors. So it says which functions were running while the Go routine was blocked. Also, interesting to see in this case is that there are spans like this one, where the program was crunching something in CPU for 11 milliseconds. And I could check which requests were running at this time. So I could scroll to Go routine and see that at about 1.4 seconds it was executing this task, and it was encoding a request. So okay, you can use same for Go routines. You can check which were running, and you can also do some like check a flame graph of yeah, it requires that you select stacks. Okay, yeah, and if you have like a number, a Go routine ID that you want to inspect, you can navigate to it just like by going G. Okay, let's back here. There are other tools that you can use as well. So, for example, if you are writing your own tools for reading the traces, it helps to convert the trace to a text so that you can grab this. You can, of course, use a library that we have since Go 122 as well. And that allows you to read the events, find out whatever you need for the case you are inspecting. Now this library was used by the multiple people to create their own tools. Some of them are experimental, some of them are usable. So let's go through some of them. One of the repos that you can find at GitHub is Go Tracing Toolbox, which has two tools usable with version 2 traces. This is an improved version of the text formatting stuff, so you can select which things to show, which things to omit, like the stack traces. There is another tool that can visualize Go-routine states. Then there is SQL Prof, which is an experiment by Felix Gessendorfer, and it imports the trace data into an analytical SQL database, and you can do queries to find out which state or like which go-routines were waiting for most of the time. And of course, you can use a Jupyter Notebook to show graphs of metrics that you need. Like, I don't know, if I wanted to see a granular graph of latency or stuff like that. All right, so to recap, runtime traces can provide you data that other tools can't. They have improved a lot in the last 2 years. And yeah, there is GoTrace UI that I think is much more intuitive, at least for me, than the original tool. So yeah, it's a great time to try out the traces, and since they will be integrated into the runtime directly, you can provide more feedback at the Go GitHub. And yeah, if you want any information about the traces, you can email me or follow me at LinkedIn. You can watch the code KiwiCon blog. And yeah, let's try the traces, and then we'll continue with the Lego set. Thank you. Any questions?
I'm just curious, you mentioned that you find the culprit behind that long query. What was it actually in the end? Yes, maybe I missed it, as you showed some traces, but what was the culprit?
Like in this case, if you mean the place where there was a garbage collection and there was a lot of CPU activity, it was that surge of requests came in, and the requests loaded data from database, a lot of data. Like, yeah, I forgot to show that in the demo. The logs showed the number of rows that was read, and there were many requests that read a lot of data, and also they processed it afterwards with CPU. So there is like processing in our service. So at the same time, it started allocated a lot of memory, and also the spans that it was processing, like 10-20 milliseconds CPU, was just crunching data. So like a really lot of work came from a single client, and it overloaded the pod.
And was there any next step from the engineering part? How to improve this situation?
Yeah, so in this case, I reduced the Go GC because we had the load higher. And also, a thing that we haven't fixed yet is the source in the client that is calling us.
I would like to ask, so this runtime tracing is like looking at the code under a microscope, should I first do the profiling, and if I don't find anything, then do the runtime tracing, or what would you suggest?
Yeah, like
Relation here.
it provides a different data. Like the profiles are aggregated, so if you can spot that after a release something is doing a lot more CPU, then it can like the profiles can help you. And if you don't see anything in the profiles, you can turn to runtime traces because it provides a different view. Like the profiles are aggregated, and in traces it's really detailed, but yes, it's much quicker to, if you can see what is happening from the metrics, probably you have already the dashboards with everything, so.
Maybe one more.
Mm-hmm.
How do you collect these traces from the machine? Manually, you connect there, or there is some tooling that's included somewhere?
Yeah, so the runtime trace package provides you just start recording and stop recording, and the start you provided the writer. So it writes to this writer, and you can store it wherever you want, to a file or a bucket or something. The flight recorder also writes to a writer. So when you stop it, it will write there. You can store it everywhere you want. And yeah, I guess that's probably the best because you can choose where you want to store it. Oh, and there is also like since the beginning the HTTP pprof endpoint there that basically calls start and writes the data to the response.